Here we go. We are talking about first law of thermodynamics. Um, so I could have given you a pre-quiz, but I was like, we'll just pick it up on Monday. So here we are. Monday, we're gonna pick it up. Okay. All right. Got to give you some terminologies, some vocab, some be able to speak the language here. So temperature. This is a measure of the average amount oops, of kinetic energy of molecules in a system object. It's the average amount of kinetic energy of molecules in a system or an object. Good there? All right. Internal energy. This is the variable for that is U. This is the total amount of kinetic energy of the molecules in a system or an object. The total amount of kinetic energy molecules in a system or an object. Absolute zero is when your temperature is equal to 0 Kelvin. No motion molecules. So this equals, so internal energy is equal to 0 joules at absolute zero. So temperature and internal energy both have to do with kinetic energy, so they're related, but this is the temperature is the average versus the total amount of kinetic energy. Okay, here's an analogy for the distinction between the two. So temperature is the average amount of kinetic energy molecules have of substance. So we could relate that to the average income of individuals in the United States. We'll say annually 60,000, the average income for individuals in the United States. Okay. The internal energy is the total amount of kinetic energy. So in this analogy of money, this would be the United States gross national product. All in this year, how much is, you know, adding all of our incomes together, what is that? that make sense? The difference between temperature is the average kinetic energy and the internal energy being the total. Under that? All right, so change in internal energy. Well, we don't really care about more or less like how much internal energy there is, but what we do care about is how it changes. That's really what we are focused on. Okay. So go ahead and leave your bag and put your cell phone in your bag. So change in internal energy is delta U. The unit is energy, joules. When is internal energy positive? Change in internal energy positive. When the temperature is increasing. Okay, when the temperature is increasing. So it is negative when temp is decreasing. Now I recognize I just made this distinction. Temperature and internal energy are not the same thing. Very true, but they are correlated. As the average income of the United States increases, so does the gross national product. Does that make sense? They are related, not the same thing, but they definitely are related. Can you take it in here?
Maybe, or could go to a study hall.
Okay, I can take you to different. What's in your pocket? Next up is heat. Talked about this on Friday. Variable for heat is capital Q. It's also a form of energy, so joules. Common misconception. Hot objects contain heat. Not true. Hot objects do not have or contain heat. Okay? Hot objects have a lot of internal energy. Okay? Heat is going from hot into cold. It is the energy of in transit. It's the energy being transferred. Okay, something does not have or possess or contain heat. So on Friday, you went around touching different materials. Okay. And those objects were colder than you. So heat was leaving you, like you're transferring heat going from your hot hand to the cold desk or whatever you were touching. Okay. Which causes your internal energy to decrease a little bit and causes the internal energy of the desk to increase just a little bit. Does that make sense? But something does not have or contain heat. It's just the energy in transfer. Good as that. It's a subtle thing, but it's just kind of how we categorize things. You heard that? Okay. Heat is considered positive when heat is added to the system. Okay. Heat is considered positive when heat is added to the system. What would have to be true for this to be the case? The environment is hotter than the system. And the environment is hotter than the system. So if you are the system, in order for heat to be added to you, heat has to go from hot to cold. Which one has to be hotter? The air around you, the environment. Get to that? Okay. So tell your neighbor when heat would be negative.
It was. Yeah. Very cold. Yeah. Like I walked in there like, geez, it's cold. Yeah. Gosh, cold. It's cold.
Okay, when heat is taken away from the system is hotter than the environment. Many of you complain about that the system is colder, sorry, that the environment is colder than the system. That makes sense? So you put a sweatshirt on. Good with that? All right. Third variable that we're going to focus on is work. Variable for work, capital W. Unit is also in joules. Work is positive when work is being done by the system. Work is being done by the system. Now, if you have ever taken an advanced chemistry here, whether that was honors, Chem 2, AP Chem, there's an inconsistency in the sign for work, how chemistry teaches it versus physics. The reason being, chemistry focuses on what happens to the system. Physics takes more of an engineering perspective and saying, what can the system do for us? So that's the reason there's a disconnect. So I apologize if you're like, that's why. So our system, a lot of times in this unit, is going to be a container of gas. And in that container, sometimes that container, the lid to that is movable. It's like a piston or a plunger. Think of like a syringe, like one of those squirter things. And you put your thumb over the end of one of those, and you can like squish the plunger, that piston stopper thing. That inside there, that's kind of what we're thinking as the system. Okay. Work is being done by the system when if it's expanding. When the gas, I should do this. When gas is expanding. So tell your neighbor what would cause work to be negative. When work is being done on the system, when gas is being compressed. When the gas is being compressed. Okay, here is a way to remember this. Okay, in physics, we care about what the system can do for us. So when we're expanding, it's like dun da da, doing positive work. I'm expanding. I'm doing stuff. Positive work. Versus compression, doing negative work, is like no, no, getting work done. Okay, negative work, positive work. I'm doing stuff. Oh no. Okay, there's a freebie for you. Hopefully you can memorize that. Okay. Okay. You're welcome. All right. Now, first law of thermodynamics says this. Heat is equal to the sum of change in internal energy plus the work. And that is it. Okay. You can't get simpler mathematically than that. Okay. It is super easy. The downfall is going to be how well you're able to identify if change in internal energy is positive or negative, heat is positive or negative, and work is positive or negative. Okay. You good with that? Like that's where the difficulty is. The math is super easy. Don't worry about this last line. How does this relate to conservation of energy? This first law of thermodynamics is the mathematical representation of conservation of energy. Okay. Last semester we talked about conservation of mechanical energy. Mechanical energy is just a subset of energy. Okay. Macro size, like any type of energy that you want, energy. Okay. This is a mathematical way to talk about the conservation of energy, like everything. Okay. So we're ending physics with this general idea talking about energy. Any type of it is captured in this.
Didn't you say you were completing like this kind of test final? There were going to be like a section specifically about this.
Yeah.
It's like a large chunk of it.
Not a large chunk because we're only spending 4 days. Yeah. It'll probably be about equal equal number of questions per chapter. Okay. All right. So go ahead and give this example problem a shot. Okay. Work done. Is work positive or negative? Done on the system. We have a negative 500 joules of work. Okay. 400 joules of heat, positive or negative? Taking away, so you have negative 400 joules. Okay, looking for delta U, have positive 100. Okay, good with that. Math-wise, it's super easy, but you have to accurately just like define is that positive or negative. Okay, so if you have a value, you have to give a positive or negative to it. Okay, here's the story behind it, like the energy flow in or out. Okay, so um, there is 500 joules of work done on the system. Okay, and 400 joules of heat left the system, and what was left over, you had 100 joules of work to be done by the system. Nope, scratch that. There was 100 joules. of heat contributed to the internal energy, causing the system to become hotter, raise the temperature. Kind of like the story that goes behind that. Okay, it's energy accounting. Where did the energy come from? Where did it go? Okay. Tell your neighbor. Tell them why. Correct answer is A. Our system is the water molecules. What is hotter, the environment or the system? The environment is super hot. The environment's like, yeah, oops, oop, oop. Environment's the flame. System's the water. Okay? So heat is being added to our system. Okay? What about the change in internal energy during this process? Tell your neighbor. Tell them why. Correct answer is A. The water is getting hotter. The temperature is increasing. Good with that? Okay, this one's a little tricky. I'm going to kind of walk you through it. Same scenario. What about the sign for work? The sign for work is 0 because there is no change in volume of the water molecules. Okay, so you're looking for, is the system expanding or being compressed? In this case, there's nothing of that going on. This is before it starts to boil. So like the volume of the water remained constant. So there's no work done. Okay. Are we good with that? Okay. So, um, so the storyline goes like this. Heat is being added from the environment to the system. There's no work. Uh, there's no work done. Therefore, you're increasing your internal energy. Good with that? Okay. Now, next scenario. Correct answer is which one's hotter? the environment of the system. Environment's still hotter. Flame is still hotter than our system. Okay, that. Fire's hot. Hotter than water. Okay with that. Okay. So A, we're going from before it boils until it boils. Is everybody okay with A? Okay, we're raising the temperature. And then we've added a balloon on top to keep all of the water molecules together. Tell your neighbor for sign for work. Correct answer is A. We're expanding. We're blowing. We're like we're blowing the balloon up. We're doing positive work. Okay. So here's the story. Okay. Heat is being added to our system. That energy is going to increasing the temperature, increase the internal energy, and we're using that energy to do work by expanding the balloon, blowing up the balloon. Good with that? Okay. Now, this is a quick chemistry review. This is one of the things that I'm like, I use this on a weekly basis. Tell your neighbor. Correct answer is C. Okay. Do you remember when you had this is classic chemistry experiment? You start with a beaker of ice with a thermometer in there, you stick it over a Bunsen burner, and while it is ice water, it's maintaining 0 degrees Celsius, like it plateaus. Okay. And then once all the ice is melted, then and only then does the temperature start to increase. Climbs until it starts to boil, and then it plateaus while it's boiling. During phase changes, it's plateauing. After it all turns to gas, it would start to climb, but you didn't have any steam in there to measure that. You couldn't. It's like, okay. But so on cooking instructions, when you're like boiling water, it says bring it to a boil and then reduce to simmer. Okay. The temperature of that water is 212 degrees Fahrenheit, regardless if you're raging, boiling, or simmering. So save some energy and reduce it to simmering. All you're doing with raging, boiling is converting like the liquid into gas faster. That's all that does. It doesn't make it hotter. Good with that? Okay. All right. Now, something that is really helpful is if we can make one of these variables 0. If we can make one of these variables 0, then we can, if this is negative, then this mathematically has to be negative. We can come up with some definitive conclusions based if one of these three are 0 mathematically. So that's a real helpful thing. So some things to watch for as you're reading problems are these things here. So heat naturally goes from hot to cold, but that takes time. Okay, for heat to go out of hot into cold. So if the process happens quickly, like if it was a rapid thing or like it happens suddenly, like I was just trying to wake people up. It worked. um, Heat doesn't have a chance. It's like, come on, give me a chance. But if it's quickly, rapidly, in a short period of time, it doesn't have a chance. Okay? So so Q is 0. Okay? If the temperature has the same, if the system is the same, has the same temperature as the environment, it's a thermal equilibrium, heat doesn't transfer. Okay? Q is equal to 0. If there is no change in temperature, like it stays throughout the process, the temperature remained the same, delta U is 0. And if there is no change in volume, there is no expansion or compression, then work is equal to 0. This is worth taking a picture or writing down. That slide there. So those are key phrases, situations that will be a real helpful thing in drawing conclusions. Okay. All right. So have a demonstration. Boom, 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 boom. Okay. What I have here is a cylinder. I'm going to stick a little bit of cotton from a Q-tip. I'm going to stick it in here in the cylinder. Get in there. And then what I'm going to do is rapidly compress this. Watch down here. Here we got a visual. Like move so you can at least see this, because so it's a one-time thing. Ready? What? 3, 2, 1. So anticlimactic. That was like I had the build up and then nothing. Wait for it. Should delete that. That stinks. Hold on a second. Need some fresh air in there or something. I don't know. Come on, buddy. Yeah. So it's worked every time since. I know, right? It's like, yeah, Smiley's demos never worked. Okay, ready? 3, 2, 1. Oh no, you didn't! Ah, 3. Take 3. Lame. Oh, so. Trying a new piece of cotton. New piece of cotton. I'm going to blame it on the cotton. Okay. Here we go. Third time. Gonna make this happen. Make some dreams come true. Ready? 3, 2, 1. Yes! There it is. It was the cotton. It was the cotton. Okay. Man, that was rough. All right. So you can figure out. All right. Have a conversation about this question. Okay. Is work positive or negative? Or zero? Negative. Why? Being compressed. Getting work done on the system. Like, no. Okay. Was internal energy positive, negative, or zero? Positive. What was the evidence? It got hot enough to burn the cotton. Okay. Was heat positive, negative, or zero? Zero. Why? Happened quickly. Correct answer is A. Now, check this. This is really important. A lot of people want to say that heat is positive because it got hotter. That makes sense, right? In order for heat to be positive, what has to be, which one's hotter, the system or the environment? For heat to be positive, which one has to be hotter? The system or the environment? The environment must be hotter. Was the room ever hotter than inside the cylinder? No. If anything, heat was negative, not positive, because the system at some point was hotter than the environment. Okay, but it happened quickly, so it didn't have a chance to do that. Here's what I want you to catch. You can change the temperature of the system without adding or taking away heat. You can change the temperature of a system without adding or taking away heat. You can change the temperature by adding or taking away heat, but it doesn't have to be that. It could be done by work. Does that make sense? That's kind of a new idea. Like, we're all good with adding and taking away heat changes the temperature. Easy peasy. But making this connection here that that zero doing work is going to change the temperature. Okay? Last demo. Feel the temperature of this can.
Jackson. What are we doing?
We're good. We're good. We're good. It's recoverable.
I have that. I just I was told it's not spirit off. Don't. Oh, you turn it upside down. Me and my dad.
Oh, okay. I thought I had to do something that was scary. 4.
Wait, even without turning upside down.
Okay. Now I'm going to. Here's what you do. You take this. You touch it. Like, wow, that's like room temperature metal. Okay. And then I'm going to spray it. And you're going to touch it and feel the temperature. Touch the can.
Okay. Oh, wait, that's quick. Oh. Wait, I forgot to remember how to remember it was last time.
It was warmer than last time.
Chili.
Oh.
See, you embarrass yourself every day.
I know.
Okay.
Wait.
Well, it's cold.
Okay.
Mom asked me pressure.
Sorry, JP. My bad, dude. I'm struggling, man, over there. So I feel that I'm like, wow, that's cold. Okay. So go ahead and figure out what's going on thermodynamically. Okay. The system is the molecules of gas. Positive or negative work or zero work. What do you think? Positive work. We're expanding. The gas molecules are expanding. Okay. Internal energy did what? Decreased. It got colder. Heat. Positive, negative, or zero? I didn't say quickly. Did I say not quickly in here? Me too. I'm looking for it. We're going to say that happened quickly. Okay. So heat was 0. Correct answer I was going for was A. Now, here's the thing. Ready? It got colder, but it didn't lose heat. Couldn't have. In order for you to lose heat, what has to be hotter? The system has to be hotter than the environment. Was the bottle ever hotter than the air around us? Never was. If anything, heat was added to the system. If anything. Because the system was colder than the environment. You good with that? So watch yourself on that. Correct answer is A. Okay. You got a worksheet due tomorrow.